In the name of the Father, the Son, and the Holy Spirit. Amen. Blessed Trinity, we love you, we adore you, and we thank you for your many blessings, for the gift of life, for family and friends, for faith, hope, and charity, and for having us here this morning, Lord. We ask that you bless us, bless our gathering, allow us to continue to go deeply into the study of nature, our human nature, and the nature that surrounds us, so that we may respect it, protect it, and promote it, among others, as your creation, Lord, and also a reflection of your love for each one of us. We pray in a special way for those who are in most need of your divine mercy, in the name of Christ our Lord. Amen. Father, Son, and Holy Spirit. Morning. This little handout over there. Okay.
Your grades. Your grades at school for your students.
Oh, for them, for those people.
Those great, those people.
Yeah.
Those,
Yep. We're coming to the end.
those other students.
You guys are all set all done?
Yeah.
I thought you were talking about statistics.
Okay, morning, welcome. Okay, just getting started. And we have today cycles. We're going to be looking at natural cycles and human recycling. Not the recycling of humans, but the recycling of human trash, all right? Which, interestingly enough, you know, of all the species on Earth, we are the only ones that actually produce trash. Other living beings, they produce organic waste that gets recycled. So as far as nature is concerned, nature doesn't really know trash except for the human that produces it. Huh? And some of the trash that we're producing is a problem because it's toxic and it's a concern. All right, so the first half of this lecture, today's lecture, is going to be looking at natural cycles. And then the second half, recycling of our trash. With regard to natural cycles, again, you notice that for the purpose of study, we defragment stuff, or we fragment it actually for the purpose of study, but in nature, all of these processes occur simultaneously in a complex and elegant interaction between them. For example, the last several lectures, we looked at geology, the formation of the Earth itself, and most importantly, the lithosphere, which is the rock formation on which we live, the crust. Then we looked at the atmosphere, the gaseous part of the Earth. And then we looked at the hydrosphere, the liquid component, but truly those three work together in a dynamic interaction to allow for life on Earth, all right? Now we're going to be looking at cycles, and we're going to go in some cases at the molecular level, especially of four main substances that are necessary for life on Earth, namely water, carbon, oxygen, and nitrogen. These are four main compounds that we need in order to live on Earth. For all living beings need these four major compounds: water, carbon in some form, oxygen, nitrogen, which is form part of the atmosphere. And then there are other substances also like sulfur, phosphates, nitrates, well, nitrates would be not nitrogen, but other compounds and elements that we also need for life on Earth. And they are clustered here in this other group. So if there are no questions or comments from previous lectures, I'm going to go right to it. Starting with the water cycle. The water cycle, as you know, liquid water is that basic compound that allows for life on Earth, because when we talk about organic life, right, it's essentially a soup reaction that is happening within the cell, and when we put cells together in that hierarchy of life into the living organism, we find that we are mostly water. Most organisms that are living are mostly water. In fact, part of the aging process is the inability of cells to retain their water. It's part of the aging process at the organic level. All right. So here we're going to see a lot of processes. There are essentially about 10 processes that happen for water to get recycled naturally through these three areas: the lithosphere, the hydrosphere, and the atmosphere. Okay? And you're going to find that a lot of these processes end with a tion, so we're going to see a lot of tions. All right? We're going to start with the first one, which is evaporation. I listed them here because they're hard to see on this diagram. But we start with evaporation. Evaporation, which is, oh, and by the way, water in the natural cycle will go through its three states, right? Which are, again, what?
Solid, liquid, gas. Yeah.
Solid, liquid, and gas. All right? So let's say we start with liquid, going to go to gas, and then turn solid and melt and go liquid and gas, and it's going to go round and round and round, depending on where it is on Earth and what kind of temperature there is in that place that is going to determine the state of water. So let's start with evaporation. Evaporation, which is turning water from what state to what state? Exactly, from liquid to gas. So the big evaporative process is happening on the surface of the ocean, all right? Which at the surface is at least how much, what percentage of the Earth, of the sphere of the Earth? About 75, I think it's about 78%, but it's about 3/4 of the Earth's surface is water, is oceans. So there's a lot of evaporation happening at the surface of the ocean. And keep in mind, when that water evaporates, turning into gas, right, into water vapor, slowly but surely, as those individual molecules break the surface tension, right? What is it that evaporates? Is it salt water? Is it water with hydrogen, with sodium chloride dissolved in it? No, it's just water. H2O molecules are coming out of salt water, all right? So it's important to keep that in mind when you stand on Miami Beach and you look out and the water's evaporating, and you don't see it evaporating with the naked eye, but we see the effects of it, which is the second stage. What happens to that water vapor as it rises? It cools, and as it cools enough, it's going to start condensing, right? And condensation will make clouds, and we'll see the clouds. In fact, you stand in front of Sophie or whatever, and you'll see a row of clouds in front of you toward the horizon, and it kind of lines up. What is that lined up? What is on the what is happening at the level of the ocean? Okay, in front of Miami Beach, when we see that row of clouds, it's almost like a river of clouds. That gives it away. What's happening at the level of the ocean? What are those clouds following? They're following the Gulf Stream, which is occurring. The Gulf Stream has been described as a river of salt water within the ocean, right? Which has a different density because it's coming from the Gulf Stream. It's warmer. It's coming from the Gulf Stream is coming from the Gulf of Mexico, through the Straits of Florida, up the peninsula, right? And typically those clouds are following the Gulf Stream and moving in the general direction of northwest, which is the prevailing wind for us, coming from the southeast. All right, so we have evaporation from the ocean, which is the major contribution to the water cycle. But then there's also evaporation on land, either from lakes, rivers, but also from the soil itself, all right? There's another type of evaporation, if you will, but actually it's water loss from animals and plants. And that is evaporation, or transpiration. We transpire, we lose water passively through our skin. It's part of the cooling process. And also plants, animals, plants, all living organisms lose water through their tissue. And that one is called transpiration. Okay. So combination between evaporation and transpiration. There's a third source of water vapor to add to the clouds, okay? And that third source is called sublimation. Ever heard of sublimation? Okay, sublimation is a particular phenomenon that happens at high altitudes, so there's less pressure. There's a handout there, all right? And it's an interesting phenomenon. It happens at high altitudes on mountains when there is snow and it is hit by sunlight, and that snow will bypass the liquid phase and will go right into gas phase. From snow to water vapor, that's called sublimation in the chemical world. In the psychological world, sublimation is a different story. But for chemical processes, that happens, for example, in the Rockies, in all high mountains that have snow. When the sun hits it, because of low pressure, all right, and the relationship of the gas laws, it goes from snow, which is solid water, right, ice, to water vapor, and that's called sublimation. So that is the third source of water vapor, gas, into the atmosphere as it rises the troposphere, several kilometers, until it gets cool enough to start condensing. When it condenses, we can actually see it in the form of clouds, different types of clouds. But the most significant one around here is the cumulus or the stratocumulus, which can be several kilometers in height themselves. And they're loaded, very heavy with condensation, ready to release that as soon as those condensed molecules start clustering around some kind of nucleus. You've heard about cloud seeding, right? I think they drop iodine crystals or something like that to serve as a nucleus on which the water molecules will stick because of their polarity. And then they're heavy enough, they have gathered enough mass to then be pulled down by gravity, which we call rain. But scientifically, rain is too vulgar, so we use precipitation, another ion, okay, another eon. So we've gone from liquid to gas by evaporation, transpiration, and sublimation. Now we go, or in case of sublimation, is solid to gas. Now all that gas is condensing into precipitation. All right, another one in the meantime, transportation. Yes, transportation is simply the air circulation, the air patterns that we saw in previous lectures, how the clouds generally move from the ocean inland. And when they make that shift from ocean to inland, the temperature is also going to change because there's heat rising, more heat rising from land than from water. And that makes them condense further, and we have precipitation. Okay? So we're here now in the second half of the cycle is going to be a downward motion. The first half has been up and transportation across. Now the downward motion beginning with precipitation, otherwise known as rain, all right? And now deposition. Depending on where the precipitation falls, if the precipitation falls on high altitudes, it may fall in the form of snow and then will gather as ice. When it gets very, very thick, it can actually form glaciers, which can be, several miles thick. And eventually, at the edge of all that ice, is going to start melting, going back into the liquid state. And now, being a liquid, it's not going to hold its own volume, right? Rather, it's going to be reacting to gravity and follow the course of least resistance, down, 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 seeking the center of the Earth, which is never going to get to the center of the Earth because it's way too hot there. But there's a downward motion by deposition, infiltration, and percolation. All this is within the soil, within the rock. Okay. Runoff either from rivers or lakes. Eventually, it can get into the soil, down into what is known as the water table. For example, the Biscayne Aquifer in South Florida, that is our source of fresh water. You have to, with the eye of your mind, follow the water molecule down, down, down as it's reacting to gravity and into the soil wherever it fits, whether in small or large volume, deep into the earth until essentially it's going to hit some kind of rock and then continue to slide on that rock and mostly end up eventually back into the ocean by way of groundwater or just river runoff. So you got surface flow and the mouth of a river on the ocean, that's called what? A delta. Or if it's groundwater, out into the ocean again to start the cycle anew. So in the second half, beyond precipitation, we have deposition, layering out, for example, snow, and they can take the ice cores year after year, what that snow picked up on the way down, right? It can tell us something about the weather and climate in previous ages. Then infiltration and percolation right through the rock and soil, snow melt until we get close to the shore. There's also going to be the uptake of water, that 1% of the 1% of the water on Earth, which ends up in living organisms, mostly plants, but also animals, as they suck up the water. And that one is going to be absorption, which is not labeled here, but I wanted to keep the churn going on. So absorption is the water that is taken up by living organisms. Interesting little detail, for example, if we picture, I don't know if you've all been to the Coconut Grove area and the South Miami, the Miami Avenue area near Mercy Hospital and further south going on Miami Avenue, there's a little park there called Kennedy Park next to the bay. You may see at some point some rocks on the west side of Miami Avenue that are smoothed out, but it's about 1 story high, and it's porous rock that is smoothed out, all right? I'm calling those the Miami waterfalls. There used to be waterfalls here. If you can picture, go back 100 to 150 years ago, there was basically no modern civilization in Miami or along the East Coast. The Everglades essentially came all the way to the shoreline, and that's fresh water that was emptying constantly into Biscayne Bay in its natural state. Because why? There were no canals, right? The canals were dug up in the 30s, 40s, or 50s, something like that, by the Army Corps of Engineers to drain off the swamp, the supposed swamp, right? On Miami land, where we stand right now. And so the Everglades essentially came up to the shore, and where it found some resistance by porous rock, the water just built up and then flowed over that rock over eons and smoothed it out. So we used to have small but real waterfalls in Miami, okay, in the South Miami. It is, it's amazing.
But you know the Verdine's house?
Verdine's house.
People who Verdine's or starting Verdine's.
Okay.
They right on that same road you talk.
Yes. In the Grove.
Attorney bought the house from the Verdine family.
Okay,
So I used
interesting.
to go to this house quite often.
Ah,
And I for wonder, the thing sits about 8-10 feet above the road.
yes,
The
exactly.
house, and they didn't build it up. It's built on that same rock.
Exactly. That's a natural cliff. I should talk a little bit about that at some point. I don't have time today, but I want to devote it more time because it's fascinating. But with regards to the water cycle itself, what I wanted to point out is that there was so much fresh water in South Florida accumulating from the rainfall, the constant rainfall that we have. And of course, there was no uptake, there was no absorption, either from agriculture, which take up a lot of water, or from just urban living, the water faucet and the showers and the toilet flushing, right? None of that. So there was abundant fresh water in South Florida that was just emptying out into the ocean. but there was so much water percolating through the porous rock that we have, the limestone, right? That also the water table, the groundwater, was very abundant and pushing hard out into Biscayne Bay, to the point that there were springs of fresh water coming out in the middle of Biscayne Bay. You can mostly walk most of Biscayne Bay. It's about 5 or 6 feet deep, most of Biscayne. Like, for example, if you stand on Brickell out to Key Biscayne and that area and the southern part, Dinner Key and the Grove area, that's fairly shallow, all right? It's all grass, turtle grass there. And periodically there were holes through the sand, there were holes and freshwater springs coming out. Okay, and there's some evidence that the native Indians here, the Tequesca, would go out in canoes and pitch a pole next to those freshwater springs. And in their canoes, they would fish for several days, and they had a source of fresh water in the middle of the bay, surrounded by ocean, okay? They had a source of fresh water coming out from these springs to drink, and also they'd be fishing because there was because of the shifting in water density from the fresh water out to the salt water, that creates a dynamic system for fish to gather and so forth. So there's abundant fishing in those water holes, all right? One day, maybe we should make a field trip to the Museum of Miami, to the Historic Museum of Miami and the prehistoric. It shows the prehistoric age. Very interesting, but it was like, if this was Biscayne Bay, there were springs of fresh water coming out in the middle of the ocean. Very interesting, fascinating. All that has dried up now because of urbanization and agriculture. But there's still the Biscayne aquifer, which is the source of fresh water for us, and that is the groundwater, all right? Okay, so very interesting dynamic and complex cycle of water as it goes through the 3 phases throughout, and this occurs all over the Earth, the surface of the Earth. Let's move forward now to the carbon cycle, which is very different than the water cycle, right? The carbon cycle, we can look at it at the cellular level or at the level of the of nature, of the environment. So let's start first at the cellular level, because it's going to be basically a chemical reaction. It's actually 2 chemical reactions that go back and forth using 4 molecules, a conversion of 4 molecules back and forth. And that is the photosynthesis and the cellular respiration, okay? So let's start with photosynthesis first. These are done in 2 particular organelles that are inside living cells. Now, only plants have chloroplasts, but plants and animals and other species like fungi, they also have mitochondria. These are 2 organelles. Remember, organelles are little structures inside each cell that have a particular function. For example, the nucleus holds the DNA. Chloroplasts, they photosynthesize. Mitochondria, they do what is called cellular respiration. They're the powerhouse of the cell. For the scientists in the group, this is basic. For the others, it's a little more involved. But basically, we have this interaction between 4 molecules. We got carbon dioxide and water on one side, and then we got oxygen and glucose on the other side. So this is how it works. Starting with photosynthesis, okay, the plant absorbs water from the soil and carbon dioxide from the atmosphere, right? And with the light, which naturally is from the sun, converts these 2 molecules, transforms them into 2 other molecules by a chemical reaction. That chemical reaction is called photosynthesis. It's a synthesis of molecules using photons, using light. So the end product of photosynthesis is 2 different molecules. On the one hand, glucose, which is a carbohydrate. Here's a carbon, here's a hydrogen, glucose. And as a byproduct, oxygen, diatomic oxygen, O2, which goes back into the atmosphere. Okay? The glucose is retained by the plant. The oxygen is pumped into the atmosphere. And this cycle of photosynthesis goes on and on and on as plants absorb, again, water from the ground, liquid water, CO2 gas from the atmosphere, through the chemical process of photosynthesis, transforms those two molecules to two different molecules, the glucose, which the plant stores, and diatomic oxygen gas, which is pumped into the atmosphere, all right? And so that's why we say that plants are producers. They're producers in the way of food, but also as a byproduct, they are also producing oxygen or releasing oxygen into the atmosphere, okay? And at the same time, absorbing CO2. We call that sinking carbon into specifically the glucose molecule or the tissue of the plant. All right, the opposite reaction happens at the level of the mitochondria. And I mentioned that mitochondria are in animals, but they're also in plants because plants are also living, meaning that they need energy to live, right? And the mitochondria are the ones that are recharging the energy molecules of the cell, which I spoke earlier is known as adenosine triphosphate, or ATP for short. Don't worry about that for now, but basically cellular respiration is the opposite, the complement of photosynthesis. In other words, it starts with glucose and oxygen. The glucose coming from the bloodstream, coming from the digestion of food, and oxygen coming through the lungs from the atmosphere. This is down to the cellular level. Each cell of our body will process these two molecules and essentially burn the glucose, burn up the glucose. That's why it's an oxidation reaction. It burns up the glucose and breaks it down into carbon dioxide and water. And in that process, the energy that is stored in the glucose is released for doing work. All right, so that chemical energy, which is a type of potential energy, is released for doing work. And that process of breaking down glucose with oxygen, all right, is called respiration. It's at the level of each individual cell in our bodies and every living organism, so it's cellular respiration. And you see that the products of this reaction is going to be precisely CO2, which is then released through the lungs, again out into the atmosphere as gas, and water, which will evaporate. Either we use it in the urine for dissolving the chemical toxins of our body and to get rid of toxin, or water that evaporates through the skin, as we saw earlier. So you see these two reactions go back and forth and they complement each other. Here is the chemical representation of this. It's called a redox reaction because it's an oxidation, a reduction, oxidation. So together, redox, reduction, oxidation. The oxidation is when oxygen is involved, okay? In other words, glucose is oxidized, burned up. That's why for fire, oxygen is needed, right? Because it's an oxidation reaction. That is the cellular respiration part. Whereas the opposite, the reducing part, is when CO2 is combined with water to make glucose and oxygen as a byproduct. That's the reducing part. That's the photosynthesis. And the oxidation is the cellular respiration. So really what we have in this process at the level of energy is a transfer of energy. The transfer of energy goes from solar energy or light energy into chemical energy in the glucose. That chemical energy is what we call potential energy because it's available for work. Once that glucose is burned, is oxidized, that chemical energy is released to recharge the ATPs. And also heat is released because it's a burning process, right? So heat is released, which is part of maintaining our body heat. That's part of it, and the heat that we release to the atmosphere. So there's a transfer of energy from light into chemical energy, which is potential energy, eventually recharging ATPs, and heat energy. And the heat energy goes out into the universe to diffuse, known as entropy, or to increase the energy that is released into the universe, which is essentially unavailable for work. Heat energy is the end of the transfer of energy, all right? So just to finalize this picture here, the actual energy is stored mostly in the carbon-to-carbon bonds. As you can see, glucose is what we call a 6-carbon ring, even though the 6th carbon is off the ring, all right? But it's a 6-carbon ring. And the largest amount of energy is stored in the bond between the carbon atoms, which are known as covalent bonds. Okay, a little too much detail, but this is at the chemical level, the reaction itself, the complementary reactions, the redox, photosynthesis, cellular respiration. Let's back up now out into nature, all the way down from the chemical through the cellular out into nature. The carbon cycle in the big picture, all right? I got down to the carbon cycle in the smallest picture, which is at the level of molecules. Now, let's back out into the big picture. We have essentially two flows, and this is similar to water in the sense that the first half of the flow of water is rising from liquid to gas, and the second half is lowering from gas back to liquid and temporarily solid in the cold areas, all right? So similar to that, analogous to that, carbon will also follow that kind of cycle. There will be rising carbon and there will be sinking carbon, all right? So the rising carbon is typically in the form of CO2, which is gas, naturally at room temperature or at ambient temperature, room temperature. Room temperature in Miami is lower than ambient temperature, right? Maybe 20 degrees. Okay, but CO2 in its ambient temperature, it's a natural temperature in the atmosphere, is a gas, as we know. And there are several sources, several sources of CO2. Let's start with the natural sources. Respiration, which I just talked about, cellular respiration, which happens in animals and plants. There is also CO2 from geological activity. For example, the volcano in Hawaii right now that keeps going and going. All right, significant. Kilauea. All right. There's natural combustion, fires, and so forth, which in nature, by the way, all these phenomena in nature are good. All right. If there were no people living on Hawaii, all of the islands, the whole archipelago, is a volcanic archipelago. So it was made by volcanic activity that came from the bottom of the ocean up until it eventually broke through the surface and formed islands. And those islands, over eons of time, with erosion, eventually got populated with plants and animals. So that's why I say in nature, there's no trash and there's no tragedy. Everything is recycled and everything has a benefit of some kind. Even wildfires. Wildfires tend to kill the underbrush that allows for trees to establish better, okay? And that's exactly what we need in our forest here, this pine forest that we have. It's getting full of invasive plants, and what it needs is a good burning, but we can't do it because it's an urban forest, it's in the middle of the city. But that's what it needs, is a good big burning to get rid of all those invasive plants that are cluttering underneath the pine trees.
Maybe you control burns at UCF.
Yes, thank you very much. Yes, is that the boxes, the 1 meter boxes with steel or something, with iron? Yes, I like, you actually did some of that? Yes?
We did research on it a little bit in my ecology class.
Okay.
The difference, there was much more biodiversity in the ones that were recently.
Yes, right, there you go. Okay, so that's the proof of principle, right? Because it gets rid of the underbrush. So I'd like to do that at some point here, is get into control burning of the invasive species because they're really taking over. Anyway, that involves a bigger project. So, but these are all natural contributions to CO2 in the atmosphere, and also soil respiration. Interesting. This soil respiration, well, the soil itself doesn't respire. We have to put it in quotations. But what is respiring in soil? The key word here is decomposition. Who are the decomposers? Also known as saprophytes, bacteria and fungi, right? Which are macroscopic but ubiquitous, and thank God they're around, because otherwise we'd just be piled in organic waste, you know, deep, deep, deep. And so these bacteria and fungi are constantly digesting and decomposing organic material down into nutrients that are then absorbed by the plants. And therefore, that decomposition process essentially is a cellular respiration process. And they are producing, they're metabolizing, and they're producing a lot of CO2 that is coming out just right through, because it's gas and it comes out through the soil into the atmosphere. So that's another source of CO2. But there is also man-made, human-made CO2, which mostly through industrialization, manufacturing, also the fossil fuels, transportation, and all of that industry that uses fossil fuel for human living, right? And that is the human source of CO2, which is extra, if you will, because it's not part of the natural cycle. It's man-made. On the downside, in other words, on the sinking part of absorbing CO2, we have the big process of photosynthesis, of course, that is trapping CO2 and transforming it into glucose, into organic material, carbohydrates that are incorporated into the cellular material. In fact, cellulose, the plant fiber is mostly cellulose, right? And that cellulose is a carbohydrate which has a lot of carbon trapped into it. So that's called sinking. Also, as plants are consumed and then plant material is incorporated into the body of the animal, into herbivores, whether on land or on the ocean, when that animal dies and is decomposed, that carbon also continues to sink into the land, into the lithosphere, if you will. Also through erosion, that picks up some CO2, and rain also picks up CO2 from the atmosphere and sinks it into the ocean, which is then, CO2 can also be dissolved into the ocean water, just like oxygen is dissolved into the ocean water, right? And some of that will deposit into the substratum, into sediment, sedimentation. So there's an upward motion that through a number of processes contributes to the amount of CO2 in the atmosphere, but there's also a number of downward processes that traps that CO2 back into the earth and fixes it or sinks it, like the kitchen sink, all right, sucking in the water down into it. Now, let's quantify this for a moment. And this is a composite picture here that has a lot of information. Let's start with the top. This is on an annual basis. It's called the carbon budget on an annual basis, all right? These are estimates of the movement of CO2 or carbon through nature on an annual basis in gigatons. Gigatons is a measure of metric tons is a billion metric tons, all right? So a gigaton is 10 to the 9 metric tons. It's a measure of weight, of mass. And 1 ton, I put it here, 1 metric ton is equivalent to 1,000 kilograms. We can continue to break this down. How much is 1 kilogram? Because you know what, we're not used to kilograms, right? We're used to, what is it, pounds? 2.2 pounds. So about 2 pounds, right? Yeah, you know that from the boxes. So 2 pounds per kilo, right? 2 pounds per kilo. 1,000 kilos is about 2,200 pounds. That's 1 metric ton. 1 billion of those is a gigaton. So these numbers are in gigatons, and this is at the global level. So it's really the big picture of the carbon budget. Let's look at it for a moment, and we'll start with the green numbers that are rising. Okay, so we have 2 types of arrows here. Some arrows are flowing up. They're all white. and some arrows are flowing down. So the up arrows is CO2 released into the atmosphere, and the down arrows is carbon sinking. All right. So let's look at the rise here for a moment in green, which is the natural carbon, CO2. There's CO2 produced by respiration, which is mostly the big contributor from cellular respiration is mostly from plants, because there are many more plants on Earth than there are animals. So it's about 60 gigatons. 60 gigatons from plant respiration, that CO2 released into the atmosphere from the respiration of plants, not photosynthesis. Plus about 60 gigatons also from microbial respiration, happening mostly under the earth. And this is going to be a combination of bacteria and fungi, the decomposers, the saprophytes, right? We can look at the equivalent of that in the ocean in general, overall. Respiration in the ocean, respiration and decomposition combined is about 90 gigatons. You follow? This is CO2 gas that is being produced by living organisms released into the atmosphere. So when we add this, we get 90 plus 90 is 180, and we have another 120 here. Of this, I'm sorry, this is 90, this is a different 90. For the sake of simplicity, we can keep it, for keeping the numbers straight, we can keep it to land or ocean, and you'll see how this works. Let's look at the land for now on the left hand of the screen. We said that 60 gigatons of CO2 produced by mostly plant respiration, plus another 60 from decomposers, right? That's 120. But guess what? In photosynthesis, from those plants, about 120 gigatons are absorbed and sunk into the glucose molecule, right? So that balances out. 60 plus 60 is 120, and about 120 is being absorbed by photosynthesis.
So far,
yep.
I'm not reading this. So the 120 on for photosynthesis.
Yep.
It's coming down.
Yes.
Okay.
That is sinking. That is what I just explained. That's photosynthesis. Remember, photosynthesis starts with what? CO2 from the atmosphere plus water from the earth, and sinks it into the glucose molecule.
So what's the red tree for?
It turns out that photosynthesis absorbs actually 123, so extra. In other words, it does the job of absorbing all the CO2 that's produced in land, plus absorbs a little bit more CO2, 3 gigatons more. All right, so it's about what, of 120, it's roughly about 3% more. About 3% more excess CO2 actually absorbs photosynthesis. All right, so that's a positive thing. I put it in red because it's extra, it's not produced by nature. Okay, now let's look at the equivalent in the oceans. Again, the combination here is giving us a combination respiration and decomposition. So this 90 gigatons is equivalent to the 120 over here. You follow me? This is CO2 that is released by the ocean from the respiration of fish, other living organisms in the ocean, plus the decomposition factor of bacteria, are pumping out 90 gigatons. But the photosynthesis that is being done on the oceans, mostly by phytoplankton, which is kind of an equivalent to a layer of grass floating in the upper couple of feet of water, right? On the ocean phytoplankton, which is plankton, microscopic organisms, they are photosynthesizing, so they absorb about 90 gigatons of CO2, sinking it into the photosynthetic process of making glucose. So they're taking care, nature takes care of its own recycling of CO2, both on land and in the oceans. Plus, it's estimated an extra 2 gigatons of CO2 are also absorbed by the phytoplankton. So they do their job in recycling and more, all right? So it's the red numbers that we're interested in, because the green, as you can see, well, blue in the ocean, green on land, those are recycled. 120 gigatons are recycled every year on land. 90 gigatons are recycled every year on the ocean surface, right? The red numbers are man-made. That's why I put them in red to distinguish. They come mostly from the burning of fossil fuels, from the making of cement and other land use, anything that is combustion made by humans, in industry mostly, right? It's a big producer of CO2. That has been estimated to be about 9 gigatons per year on the budget, which is small compared to the big numbers of 90 plus 120 is about 210, right? So by comparison to that, we're only producing about 9 gigatons, but keep in mind, this is worldwide. But it's extras, it's excess, because it's man-made. And therefore, how about the recycling of that? Well, of these 9 gigatons that is estimated that humans are pumping, CO2 pumping into the atmosphere every year, 3 of those 9 get absorbed by photosynthesis on land, and 2 gigatons get absorbed by photosynthesis on the ocean. 3 plus 2 is 5, to 9 leaves 4 gigatons of CO2 that is estimated to be accumulating every year on the surface of the Earth in the troposphere due to man-made activity. And that's the concern. That's the concern when we talk about global warming, because, of course, these are estimates, right, on the global level. So there's a margin of error. But the point is that we are producing an excess CO2 that doesn't get absorbed, doesn't get sunk into land from either the ocean or land or of photosynthesis every year. And that accumulates little by little, little by little. Now, what's the issue with that? Well, CO2 is what we call one of these greenhouse gases, right? Greenhouse gas, what does that mean? The greenhouse up north is when you have a house of glass, the rays of light come in, some of that light transforms into heat, and then the heat gets trapped inside the glass house. So it creates a greenhouse effect. You can have a warm glass house up north in the wintertime because it's holding onto the heat. Well, that's what happens in nature also. These molecules of CO2 hold on to heat. So they do what is called a greenhouse effect. They warm up the atmosphere. They warm up the atmosphere. As the atmosphere gets warmer, what happens to the ice? The ice starts melting, especially on the poles. And so that could be a concern for sea level rise and ice melting, and the complex dynamic of disrupting the 2 polar regions, which is where most of the ice is, plus the glaciers in high mountain ranges, okay? So the issue here is with this increase of approximately 4 gigatons of CO2 accumulating every year in the atmosphere for the past several decades, essentially since the Industrial Revolution forward, which already is more than 200 years. So slowly but surely, this is happening. It's a concern. How to deal with it? We have to get creative, and I'll show you a couple of clips at the end. It's a lot of videos, by the way. You can go online and Google this, and there are a lot of videos of people getting creative on how to sink CO2 out of the atmosphere back into the Earth. Okay, I have to move on to another cycle. Let's look at the oxygen cycle now. Oxygen cycle. Keep in mind that all these different cycles are occurring simultaneously and interacting with one another. I have separated them for the purpose of study, but this is all happening simultaneously. The CO2, the oxygen cycle now is going to be a little more complicated because the oxygen molecule is going to be either by itself or in combination. And it can be by itself, just diatomic oxygen. What we call diatomic oxygen, again, is what? Just O2, which in ambient temperature is in what state? Gas. And it's what we're breathing right now, in and out, and that's the one of the 2 ingredients for cellular respiration, right? The other one being the glucose. All right, So there's diatomic oxygen going around in the atmosphere here. It gets picked up by rain and so forth. It sinks into the ocean, it comes onto land through cellular respiration is processed. And so that oxygen gets combined sometimes into CO2. Sometimes that oxygen gets combined into water, into H2O. And even in the organic molecules, wherever you see an O, oxygen, that oxygen is being cycled through there. So you can see that the oxygen cycle is more complicated. It depends where it is. If it's by itself as diatomic oxygen, which is going to be gas, or if it's going to be trapped in water, or CO2, or other, I should have put here, other organic molecules that have oxygen in it too. So you see that the oxygen is more complicated. It depends in what molecule it's going to be. For our purpose, the most important one is diatomic oxygen in the atmosphere for breathing, for respiration. Moving forward, another element that also gets cycled through nature is the fourth one of the four main ones: water, carbon, oxygen, and now nitrogen. Let's look at nitrogen for a moment. If we go to the biochemical level, nitrogen is one of the essential ingredients for organic life because it's part of the protein molecules. Remember that proteins, we have thousands of different proteins in the body that they do the work of the body, right? We have structural proteins and functional proteins, enzymes, for example, and many other substances of the body are made up of proteins. And proteins are broken down into what is known as polypeptides. This is a chain, long chains that form either helices or sheets. Don't worry about too much detail there, but basically the building blocks of polypeptides is what we call amino acids. There's 20 amino acids in nature that occur naturally. And one of the bases for amino acids is a nitrogen atom, all right? Here represented in purple N. So this is one example of an amino acid. And this end here is called the amino group. Then the chain can be long or short, but basically there will be nitrogen forms these 20 amino acids. The amino acids are the building blocks of polypeptides. And when polypeptides come together in a three-dimensional structure, those are the proteins themselves. For example, hemoglobin, all right, is a combination of four proteins that are alike. They're called myoglobin, and that's the whole complex of the functional hemoglobin that transports oxygen and CO2 in the body. All right, at the natural level, there is a process. Most of the nitrogen is trapped, like I say, in proteins. When animals and plants die, that protein is broken down through decay and also expelled through urine into ammonia. That ammonia then is broken down further by bacteria into nitrates, which can then be absorbed by plants as nutrients through the soil, and eventually pumped back into the atmosphere. Remember that diatomic nitrogen, what is diatomic nitrogen? N2 in gas form is most of the atmosphere. It's about 3/4, I think, of the atmosphere, right, that we're breathing in and out right now. It doesn't do anything. It's an inert gas, and it's gas form. It just comes in and out of the body. But there's a lot of nitrogen, diatomic nitrogen, in the atmosphere that can also get fixed into the soil through bacteria. When we look at the nitrogen cycle in nature, we can start, let's say, with atmospheric nitrogen, that diatomic nitrogen gas, which gets absorbed by mostly bacteria, either in the soil or on the nodules of plants, especially the legumes. What are the legumes? the beans, right? They have a lot of nutrition, and these bacteria can fix nitrogen. This is the equivalent of the sinking of CO2, right? Into compounds that then are absorbed by the plants, nitrates and nitrites. Also, when plants and animals die, they're broken down by decomposers. Here are the bacteria and the fungi, which contribute to ammonium and are then further broken down by bacteria into nitrates and nitrites, which can be absorbed then by the plant for recycling. So bacteria are very important, and fungi, in the nitrogen cycle to produce the nutrients that are necessary for plants to live. And then that contributes in an indirect way to keeping the plant alive so that the plant itself can photosynthesize and do its work on Earth. So up until now, we've seen the four main molecules, if you will, or compounds that are essential for life on Earth. The four being, again, water, oxygen, carbon in its various forms, and nitrogen also in its various forms, all right? There are other compounds that are also needed for life on Earth. Most of them are minerals, like calcium, potassium, sodium, chlorine, magnesium, also sulfur and phosphorus. Each one of these have their own cycles as they go through nature back and forth. And here's just a representation of human body by proportion. The human body, which is kind of typical of many other organisms that are living on Earth, is mostly oxygen in some form, the oxygen molecule, the oxygen element in some form. 65%, 2/3 of the body will be made up of oxygen. Then another 18, almost 20% will be carbon. Another 10% would be hydrogen, 3% nitrogen, and then the other 4% left from all this is a combination of all these other elements. All the way down to what we call trace elements, which trace elements means that they are in a very small amount, less than 0.1% in the body, but still necessary, essential for living, like iron, for example. Without iron, we couldn't respire, because iron is the core of a hemoglobin molecule to transport the oxygen from the lungs into the tissue, precisely. Manganese, iodine, for example, for the proper functioning of the thyroid gland, just to give an example. We have copper also, chromium, cobalt, silicon, zinc, boron, many other elements in the body, but in trace amounts, okay? So the quantity and the quality are both important. There was one last element that is significant. It's about 10% of our body, which is hydrogen, and that has its own cycle. And if you thought that these other cycles were complicated, the hydrogen cycle is even more complicated. And I'll end with this one for the first part of the lecture. What can we say about the hydrogen cycle? Is that it is ubiquitous. In other words, it's all over the place. There should be cycles, all right, properly speaking. And in biblical terms, what would we say? That the hydrogen cycles are legion, is what we say in biblical terms, right? They're all over the place. It's like little demons. They're all over the place. And for example, these are the four macromolecules, the four groups or types of macromolecules or organic molecules on Earth. What are those four types? Proteins, lipids, carbohydrates, and nucleic acids, all right? All those four molecules are full of hydrogen. It's the simplest element. You can see it on the periodic table there, number one. Look at carbohydrate, for example. Here's a glucose molecule. It's got hydrogen all over the place. Essentially, hydrogens stabilize the molecule because they link up to whatever orbit is available. They'll link up there, and so they stabilize molecules, all right? Carbohydrates, full of hydrogen. Proteins also. nucleic acids. Here is one of the nucleotides. It's a purine with 2 rings. And lipids also, fats, oils, greases, right? They're all full of hydrogen. That's what makes the difference between saturated and unsaturated and polysaturated, polyunsaturated fats. So hydrogen, really being the simplest atom and element, is all over nature in many, many, many different forms, usually to stabilize molecules. But it's in very small amount overall. Very small amount is considered in the atmosphere in this gas form. In other words, diatomic hydrogen. What's diatomic hydrogen? H2, all right? Very, very small amount. Less than 0.00005%. Okay? Less than 0.00005%. And that's a very good thing because hydrogen is highly flammable, hydrogen gas. It's light, and so it's very tempting to fill balloons with hydrogen and rise into the atmosphere. And in fact, the blimps and what was called the airships. Remember the airships from the First World War, the Second World War? Well, the Hindenburg was one of those, came close to a tower and exploded. And so it's a good thing that it's in very small amount, but that amount is sufficient and necessary to be used by all the organic molecules on Earth. And so that's why we say that hydrogen is really ubiquitous, and it's an extremely complex cycle, but it's there in a very dynamic state, being transferred all over the place. Okay, so these are the main cycles of compounds, of the major compounds on Earth. Going back to the first slide here. Now we're going to take a little break and come back and look at cycles, the human cycles or recycling, because like I said at the beginning of the lecture, nature doesn't know about trash. Everything in nature is recycled automatically all the time. And that actually has a growth effect, a net growth effect for an area that is originally barren. If one leaves it alone, eventually that area will be populated, beginning with pioneer species and then through succession into what is known as the climax community. Precisely, a great part of it is because of the recycling, all right? So there's a built-in mechanism in nature for cycling and recycling all the organic material. When we come on land and we start producing our own trash, that's a different story, because now we have, especially the synthetic materials, we'll talk about just a little anticipation, 5 types. By the way, I made a mistake in the little handout that I sent last night. I corrected it on this one. It's 5 types of materials that we're producing as trash, 5 different types of groups, of which 3 are fairly easy to recycle, but 2 of them are a big, big challenge in recycling. And so we'll look at those, okay? Let's take a break now. It's 10:25 more or less. So we'll get it down to what, 10, 15 minutes. We'll start at 20 of, 20, we'll start at 10:40, all right? For the folks online, we'll start again at 10:40, all right? Okay, so let me pause this and pick up, pause recording. Okay, folks, we're going to resume here a few minutes later. Good. Excellent, excellent. Yeah, it does take that extra effort, right? But it pays off, it pays off. I want to go back briefly to last week's lecture on the cycles and the big, since I was talking about the carbon cycle and the greenhouse effect and global warming, all that, right? And the big cycles that we have seen as recently as the past 500,000 years. Remember the Earth? 4.5 billion years, all right? And we've had life on Earth that can be traced with the cyanobacteria for maybe at least 3.5 billion years, right? And a billion is 1,000 million. So you realize that 500,000 year in geologic time is still kind of small. And we know of 4 cycles of glacial, interglacial periods. I covered this at the end of last lecture. But just to mention that this happens in the last 500,000 years. So just 2 things to point out that I think I didn't mention. Number one, we had nothing to do with these ice ages and interglacial periods, right? The winterization and tropicalization of the Earth by way of that red CO2 that we're pumping into the atmosphere, the 9 gigatons. Absolutely nothing to do with these cycles, and they were drastic to the point of winterizing the tropics and tropicalizing the poles, all right? And that's only the past 500,000 years. Imagine what has gone on previous to that. For millions of years, hundreds of millions of years, thousands of millions of years that the Earth has been around with a more or less benevolent atmosphere, okay? So these cycles are big, they're in nature, but they're long-term. So really, when we look at our stuff, we're in this little wiggles that are going on, which really in geologic time, that's called noise, all right? It's just fluctuation, even at the level of decades or centuries. It's still considered fluctuation or noise, background noise. Okay. Now, back to where we were today. So the natural cycles, put them together into the dynamic flow of nature. And then now let's add the human factor. Let's land humans on this benevolent planet with our living and the product of our living, which is trash. Tons and tons of trash all over the place. So we can think of 5 groups of trash that we produce. Keep in mind, a little conceptually first, to try to get a grip on this, but landing it realistically, this is all added stuff to the environment that is naturally not there because it's human made, right? Human products. It could be wood products, paper, cardboard, fiberboards, etc. Or they can be in the metal area, like cars, trucks, planes. Every time I drive up and down 37th Avenue to come to St. Thomas University, I go in front of Opa-locka Airport, and periodically they bring one of those old planes on the corner of the airport and they start dismantling the plane. And then across the street, there is a recycling center, very conveniently. So they take parts of that plane, chunks, and recycle it. So metals are from construction material, for example. And another large group of stuff that we have produced that needs to get recycled somehow is glass, all kinds of bottles, pane glass from construction, glassware, etc. A lot of that too. Mostly it's a silicone base. And then plastic and electronic parts. So in plastics, many kinds of plastics are mostly derived from fossil fuels, from petroleum. They're originally byproducts of the refinery of petroleum. These polymers that are synthetic polymers and make up what is known as plastic all over the earth. And then the more challenging one even than plastic, in my mind, are electronic parts. Okay, more recent decades, but basically since last century, radios, TVs, computers, phones, all that, because of what we know as built-in obsolescence, right? We're now, I think this is generation 6 and now up to generation 10. And this was about 3 or 4 years old, all right? So built-in obsolescence is that the next generation is bigger, better, faster, et cetera, lighter and thinner. And so what do we do with the previous generation? Well, we dump it because there's no way, it's more expensive to retool it than to ditch it. But the ditching, it has to go somewhere, right? It's supposedly illegal to ditch it in the oceans, even though it's happening. And so we ditch it mostly north and northwestern hemisphere is ditching in Africa, a little less in Latin America and in Asia, but mostly in Africa. So that there are these huge, huge piles of computer parts and TV parts and radio circuitry and all that, which is toxic. It's highly toxic. And when it rains, all that percolates down into the groundwater. And even before that happens, all kinds of folks go in there looking for pieces and parts to rescue. And this is a huge industry, cottage industry, highly toxic and dangerous in Africa and in India, all right, which are sadly the two poorest continents in the world. So the north is dumping on the south big time, especially toxic material by way of these electronic parts. And it's accumulating. It's supposed to be illegal, but we know what happens with regulation and corruption, right? Big concern. All right. A lot of our trash ends up in the ocean one way or another, directly or indirectly, as it breaks down and flows out into the ocean. So I'm going to revisit briefly the 5 gyres that we talked about, the 5 main gyres that we talked about in the hydrosphere lecture, which correspond to the 5 main oceans of the world. We can begin right offshore here with the North Atlantic gyre. And keep in mind that these gyres tend to be clockwise in the northern hemisphere, which is the opposite direction of the wind pattern. Remember, the hurricane pattern is opposite. So we have the hydrosphere circulates in one way and the atmosphere is circulating in a different way because it's more affected by the spin of the Earth. At any rate, there's the North Atlantic gyre. Okay. There is the South Atlantic gyre going in the opposite direction, counterclockwise, right? Picking up cool water from Antarctica, moving up the coast of Africa, warming up at the equator, and then coming down South America. So bringing warm water down the coast of South America, mostly Brazil, but also, well, here it gets stuck with, so Argentina and Uruguay have more of a cold front coming, a cold current coming up the coast. But the big one, the South Atlantic gyre, is here counterclockwise. Just for convenience, if we continue along to the right-hand side or toward moving eastward, there is the Indian Ocean gyre, which again, in the southern hemisphere, counterclockwise, picking up cold water from Antarctica, moving up the western coast of Australia and Southeast Asia into the equatorial region of the Indian Ocean, and then coming down the eastern coast of Africa, tropicalizing that significantly. Who knows what this island is, this big island here, off the east coast of Africa?
Madagascar.
Exactly. And Madagascar is a warm tropical island that is exuberant with wildlife, has a lot of biodiversity, and part of it is because it's being bathed by that warm tropical, subtropical Indian Ocean gyre, bringing warmth and rain and humidity to the area. Anyway, what's fragmented here in half is the 2 big gyres in the Pacific Ocean. Of course, the North Pacific gyre, again, going clockwise, starting, we can start here off, what do we have here? Down here is the Philippines, and further north, Japan, going up to Siberia, across the Bering Straits, if you will, down Alaska and the California current of North America, the west coast of North America, down, bringing cold water down through the west coast of North America into the tropical region, warming up again across the mid-Pacific. That forms the North Pacific gyre. And then south of it, of course, in the opposite direction, counterclockwise, is going to be the South Pacific gyre, all right? I want to concentrate for a moment on this North Pacific gyre. And so in the second part of the lecture, I have a bunch of little videos for you. They're very illustrative, all right? And because part of the issue of the gyres is that because they're rotating, then they are also concentrating. And they're concentrating the trash and the garbage that is floating on them, and that is also in the water column itself, all right, suspended in the water column, moving around into this huge twirl, and the twirl, you know, tends to concentrate stuff toward the center. So it's forming these huge, huge garbage patches. Now the garbage patches are not necessarily floating islands of trash that we can see, all right? It's mostly broken down because through the action of sun, ultraviolet, wind, and wave, and constant motion, all this trash, little by little, gets broken down into smaller and smaller fragments. And beyond that, into microscopic fibers and filaments and beads, all right? Which eventually, if it gets down small enough to the microscopic level, it can start getting incorporated into the food chain because of filter feeding animals. And then all the way up the chain, the food pyramid, with the biomass, which eventually will hit the larger animals on Earth, namely humans. So here's a little video to start about talking about these now known and famous North Pacific garbage patch, or the Great Pacific Garbage Patch. Okay, let's look at this. Most of them are short. Oh, yes.
CNN had something on one of those islands over here,
Yes.
that all the plastic was washing up on this island somewhere in the Pacific.
Part of it is washing up on the islands. You'll see the macroscopic stuff tends to wash up on islands or shores because the shores act as a natural filter, if you will, to the large stuff that floats. I'll have a few more videos on that. But the bigger concern is what we don't see, which is much larger by mass, far larger, because all of these chunks and parts of trash gradually break down, whether it's metal, wood, plastic, or glass. But the other three, you know, wood, metal, and glass tend to get recycled easier in nature. The big concern is the plastic. That's the big concern. So let's try the lights.
Plastic pollution is one of the biggest threats the oceans face today. But how much do we really know about it? On its mission to solve this problem, the Ocean Cleanup just published the most advanced research ever on the Great Pacific Garbage Patch, the largest accumulation zone of ocean plastic on the planet. Scientists have been studying this area since the 1970s, mostly by dragging a small sampling net through the ocean. The Ocean's Cleanup's researchers believe this method was valid only for small debris and covered too small an area to reliably measure larger debris. So, in the summer of 2015, the Ocean Cleanup launched a mega expedition, crossing the patch with 30 boats simultaneously. In addition to using many small nets, 2 giant trawls were towed behind the fleet's mothership. In total, they brought back 1.2 million plastic samples. All were hand-counted, identified, and classified by type and size. A monumental task, taking a team of lab technicians 2 years to complete. However, the largest debris appeared less frequent and more scattered. Quantifying the debris required an area 20 times larger than the mega expedition to be covered. Something only possible from the sky. The Ocean Cleanup ran the first ever aerial surveys of a garbage patch by converting a former military aircraft into a high-tech research platform. Cutting-edge sensors allowed them to reconstruct the 3D shapes of large debris to calculate their mass. The results of all this work? The Great Pacific Garbage Patch measures 1.6 million square kilometers. That is 3 times the size of France. The patch contains 1.8 trillion pieces of plastic, which equals 250 pieces for every human in the world. The total mass amounts to 80,000 tons, 4 to 16 times more than previous estimates. 92% of this mass is made up of the larger objects, all of which are destined to fragment into dangerous microplastics over the next few decades if left under the effect of sun and waves. And because the findings show that pollution in the patch is increasing exponentially, the plastic is unlikely to go away by itself. These results paint a new picture of the problem and provide a baseline for the cleanup of the Great Pacific Garbage Patch, set to start in 2018.
Okay, so that's one. In fact, this, you see, has a trademark tag on it. This, the Ocean Cleanup is a corporation that is one of many corporations now in the environment trying to take care of pollution in the ocean specifically. And these garbage patches, which are huge, but diffused. So they're hard. There's not a solid island that you can stand on, for example. It's just floating around. But considering the volume, then they are there, they're real. And like the video said, slowly but surely, with the natural action of light and wave and wind and temperature, all this material keeps breaking down into smaller and smaller, eventually into microscopic plastic pieces, all right, that then tend to get into the food chain. All right, so that's one issue. It's the beginning of exposing the problem. Let's move forward here. And let's stay with the microplastic for a moment, which really can be divided into two main areas, either microbeads or microfibers. These are terms that are coming up in the literature now. The microbeads as such are barely visible, but they can be visible by the naked eye, all right? So really, technically, in my opinion, they should really be called mini beads, but not micro in the sense that they can barely be seen by the eye. Also because they tend to have a color, typically blue or green or red or yellow or something like that. And it's put in many products now on purpose, in detergents, in cleaners, in toothpaste, in shampoo, because it generates a scrubbing action, all right? So those are microbeads. Different from that is the actual microfibers themselves, which are defined to have less than a 0.1 millimeter, actually this is in diameter. So this is like 1/10 of a hair, of a human hair diameter. So very, very small, definitely microscopic. And we don't see them, but they're accumulating in an exponential rate, mostly in the ocean and starting to get into the food chain. So let's look at a little video on these microplastics. This is new research that is coming out in the past couple of years. And so, as always, for scientists, observation and experimentation, right? But first we have to try to get a grip on what we're dealing with, being that they are microscopic by definition, cannot see them easily.
25 million years ago.
Yeah.
It was completely legal to dump plastic in the ocean until the 90s. And a lot.
All right, let me stop there because this is her first statement. It was completely legal to dump plastic in the oceans up until the 1990s. So, okay, I remember the 1990s. That was, it's now 30 years. It's going to be 30 years. But basically, up until a quarter of a century ago, it was not illegal to dump stuff into the ocean and to dump plastic, right? So that's the opening statement.
A lot of that plastic is still there because plastic lasts out there for a very long time. It just breaks down into smaller and smaller pieces.
So now we get into the microplastic stuff.
We know that over 300 species of wildlife have ingested this material. It's been reported in animals. And so as it is eaten by animals, it actually can move up the food web. And as it
Go back for a moment because This is a bird, or the carcass of a bird, and this is the gut of the bird. These are mostly seagulls and other marine birds. When they see, and they go after stuff that is floating. So they go after mostly bottle caps and other plastic stuff that's floating, and they just ingest it, all right? And after a while, the whole gut gets full of this plastic that cannot be processed out, and so they die, and then they die on the shore somewhere, and this is the carcass of one of them. That's the stuff that this bird has in its innards. So just one example of this plastic just not breaking down and getting into the food web.
And as the scientific literature on this issue increases, literally almost every habitat they've gone to, sea mounts, Arctic ice, coral reefs, deep sea, it's become ubiquitous. And I don't think anybody would fight anyone on an argument that plastic debris is not become a contaminant of concern.
This is Chesapeake Bay, just off the east coast of the States.
Basically a big metal box with wings. It looks like a manta ray. Very long, about 12-foot mesh net off the back. 1, 2, 3, 5. At the end of the piece we can take off, just collected all of the solid. Rinse it all out, filter it through another strainer, and then put it into a jar. Well, a lot of other stuff. You want to take a look at what's rinsing out of the stream. It's 4 tiny plastics.
What we're concerned about ultimately is what are the implications of trash going into the water, getting into the food we harvest? And we're still connecting the dots there a bit. We know that lots of trash goes out into the water. We know that the sun and waves breaks it down into small pieces. We know that many, many, many species of animals eat it. And we also know that bigger animals eat smaller animals. And we also know that we eat those big trophy fish. And so what we're really trying to figure out is how big a vector plastic is for transporting chemicals into the tissues of the animals that we eat every day.
You notice he talked about vector. How big a vector is plastic? In other words, these fibers, these microfibers, tend to be porous, and they trap chemicals, plus the own chemicals that they carry because they're made from synthetic material, right? They're synthetic plastic. They can be nylons, they can be polyester. And they carry the chemicals that were in the production line in themselves. So that's what we call a vector. A vector is an agent that transmits something that is being carried from one organism to another, all right? So that's another layer of complexity, if you will, with these plastics, not just the fiber itself that's getting into the food chain, but what that fiber carries inside chemically. And as it gets accumulated on the biomass, remember the food pyramid and the biomass trophic level accumulation? What's the ratio of accumulation? An average of biomass from one trophic level to the next? 10 to 1, all right? 10 to 1. Not 10%, but 10 to 1. 1,000% to 100%, okay? So it takes 10 pounds of the previous animal to put on 1 pound. So there's a concentration factor of 10 times, all right?
That's a big problem, much bigger than big chunks floating out into the ocean.
We don't know exactly what that plastic is. We don't know where exactly it's coming from. And if we're trying to find policy and educational solutions to it, we need to know what we're targeting. We can't just ban plastic. That's not going to work. What kind of plastic is it, and what's the best policy route to reduce it? Is it a ban? Is it a fee? Is it market change? Is it education and behavior change work? What's the best way to tackle it? And until we know exactly what we're doing here, we're not going to be able to design the right programs with this.
Right. I mean, this happened, and this is not in some far off foreign land. This is Chesapeake Bay on the East Coast. It's one of the major waterways of the East Coast of the U.S. So it is a concern. One thing that is challenging, like she says, until we know exactly what we're dealing with, we basically can't do anything about it. No, we have to act already, because certainly we can do a lot about trying to prevent plastic in general from getting into the oceans. All right. So the next few videos are going to be on recycling.
You know, Father, there was a major push about 10, 15 years ago, say in garbage bags, where they tried to make biodegradable garbage bags.
Right. Yes.
So they tore differently. Like a regular garbage bag would tear.
Right.
Horizontally.
Right.
This one would tear
vertically. Right.
And they were much weaker.
Right. Yeah. So there's a trade-off. Where's the balance, right? Because
exactly.
if it starts biodegrading from the time you get out of the supermarket to the time you get to your car, then you're gonna have your food in the middle of the parking lot. Yes. So there's a lot of R&D going on, research and development with industry, partnering with science to make these products feasible. But you mentioned something that came to mind. Should put it in here as part of because the other slide is very crowded. So I'm going to stick it in this one. Just briefly, give me a moment. The 3 R's: reuse, reduce, reuse, and recycle. Have you heard of those 3 R's? Let's see if this makes sense. Yeah. Okay, these are, they call them the 3 R's that ecologists are promoting. Let me finish here for a moment. This is kind of anticipated because we're going to get into some recycling and bioremediation. Okay. So with that said, let's go there. We can look then at some of the solutions for the problems. And again, it's a multi-pronged approach. It's not just one thing. It's not just education. It's also development, research. So it's a whole complexity of activities coming together in our social living. But 2 main areas could be recycling and bioremediation. Bioremediation. Another one of those compound words, recycling and bioremediation. So let's look at, this is a little news clip from a couple years ago of ocean trash recycling. It's 4 types of recycling that are going on. Some of it is a little futuristic, but that's part of research and development, right? News agency.
This shows you the exact image of what behind your wall. There might be a solution to the giant garbage patch in the Pacific Ocean. A Dutch group aiming to rid the oceans of plastic junk has announced it will begin efforts to clean up the Great Pacific Garbage Patch by 2018, 2 years earlier than originally intended. The organization Ocean Cleanup will use trash collectors in the form of curved booms and screens, which are suspended by anchors floating in deep water. The system will act like an artificial coastline, catching plastic debris as it drifts on the surface or just below the water. Once full, the vessel empties the system and transfers the collected plastic to land for processing and recycling.
Okay, good question. So unlike the trash, animals are more mobile. So because this is a passive system, all right, it's slow moving, it just basically moves with the currents. The idea is that the animals will get out of the way sooner or later, whether they're marine animals or flying, birds.
The group plans to deploy up to 50 systems and expects to collect 50% of the trash in the Great Pacific Garbage Patch in just 5 years. Ocean Cleanup's first pilot parts are now in production and will begin testing off the west coast of the U.S. by year's end. Say no to safe spaces on YouTube.
Sorry, it has this little advertisement in the middle.
Here's what's currently being done on the plastic menace in our oceans.
Yeah.
Feeding device designed to keep the ocean clean.
It's from the UK.
Turton and Pete Kudlinski, who are also best friends, decided to do something after they became frustrated with the amount of trash that was floating in the ocean waters that they spent much of their childhood playing in. The duo quit their jobs and invented the season, which is what they hope will be a sustainable way to reduce the amount of garbage that is polluting the world's waters.
It's a private initiative by these two fellows who designed this contraption.
The pump brings water through the season, which allows the natural fiberglass inside the device to catch the floating rubbish and debris before water is pumped back out. Users have the option of installing an oil and water separator to the pump to clean the water that flows through it before the water is allowed to flow back into the ocean. The season is lined with a natural fiber catch bag that collects floating debris. When the bag is full, it can be changed with another clean one, and the collected debris can be disposed of responsibly. Turton and Kudlinski are trying to raise enough capital to turn the season prototype into a reality. According to Australia's ABC News, crowdfunding has helped the two men raise $50,000 for commercial production, and the video of the season in action has attracted more than 10 million hits online.
So a lot of private initiative in this.
Save the planet from plastic trash.
Okay, there's a third one. So those first two we see some kind. We're in a market economy, right? So somehow it's got to make some market sense. It's got to make some kind of profit out of it to be able to make it sustainable. But one of the assumptions here is that the raw material is free, which is basically the trash. So it's all about the processing of that trash into something that can make money, or at least make it sustainable. This one's a little different. This one is, these are called wax worms. These wax worms naturally live in beehives, all right? And it's been discovered that they digest plastic. So this is an interesting little video here.
After years of trying to find a way to get rid of plastic waste, scientists have finally found a solution, courtesy of a drab little bug. Wax moth caterpillars that typically eat beeswax in hives have been found to also be capable of degrading plastic. Polyethylene is one of the most commonly used plastics, with strong carbon-to-carbon bonds that render it resistant to degradation. However, waxworms are able to make holes in a polyethylene bag in just 40 minutes, eventually eating through most of it in just a few hours. Researchers suspect bacteria in the guts of the worms are responsible for digesting the plastic and breaking it down into ethylene glycol, an organic compound. Scientists want to study the chemical process that allows polyethylene to be degraded and maybe adapted into a solution for managing the world's plastic waste. Indonesia pledges $1 billion in...
Okay, so that was the third one. There's a last little video here. So these are wax worms. This is getting into the other area that is called bioremediation. Is using natural agents to clean up an area or to try to restore an area that has been contaminated.
What is it?
Oh, those are the wax worms. You can watch later the little video. These are worms that actually they're larvae of a moth that feed on the wax from bees, okay, in bee hives. And these worms, these larvae have been found to eat through plastic and possibly digest plastic and break it down, the polyethylene synthetic fibers. Okay, you can see a little video later, or you can just put You can Google it. There are many, there are hundreds, if not thousands of these videos online in all different areas. Like you can put wax worms and plastic and Google that and you get some videos.
Plastic waste is a major global problem, and second only to China, the world's biggest source of the pollutant is Indonesia. Responsible for a massive 54,000 kilometers of coastline, the Indonesian government is about to do its part to reduce plastic in the environment with a pledge to spend $1 billion on the problem. And it is indeed a global problem, one which the United Nations has declared a war on. Each day.
Sorry.
Wow.
The previous, yeah. So China is number one, sadly. Well, of course, proportionally, China has about 1/4 of the world's population, right? And huge territory. Indonesia is the second, which is mostly surrounded by ocean, the Pacific Ocean. You see a lot of it here is this foam, the polystyrene,
Yes,
all right? That foam is a big problem because that lasts centuries, if not millennia, in the environment. It's been estimated because we haven't had it for that long, but this is all synthetic. And this is broken down, those coolers and the little cup, the polystyrene cups,
Yes,
coffee cups. Imagine how many of those are produced every year in the world. They come from a little tiny bead. It's mostly air inside, but the air is trapped inside this polystyrene. Okay, so it's all synthetic material that nature doesn't know how to handle it, except for breaking it down slowly into smaller, which then become microfibers.
Nations has declared a war on. Each day, more and more plastic finds its way into our oceans. As plastic does not decompose,
There's the 5 gyres.
much of it collects in the open ocean, driven by currents. One such concentration is known as the Great Pacific Plastic Patch. Another of these floating patches is larger than France. Scientists believe the entire mass of oceanic plastic could outweigh all the fish in the world's oceans in 30 years. And today's estimated 165 million tons of the stuff in our oceans is already getting into our food supply. There you know.
Okay. Now, we know we have pollution in the US. Do you think that any coastline, I don't know for sure, but my sense is that there's no coastline in the US that looks like this, right? Why? Well, first of all, there's a regulation, and the regulation is enforced.
We're more
It's
conscious
illegal.
of it.
Yeah, we're more conscious, but also there's regulation, and the laws are enforced. You know, in other words, I'm not going to be so naive as to say there's no corruption, all right? There's less corruption, much less corruption.
You look at the cruise lines, Farm.
Yes?
They call Carnival dumping 2 bags of garbage,
Mm-hmm.
$500,000. Fine.
For 2 bags.
2 bags.
Yeah, right?
And this
Exactly.
is On Carnival cruise lines.
Right.
So, couple years
There you
ago,
go.
2 bags. 2 bags.
Yeah.
Don't throw them over, like, yeah, 2 of them over.
Yeah, so that might be just an employee who threw it over. It was, I'm sure it's not the policy of the
No, it's not a policy.
of the ship, right? It's not the policy,
Yeah,
but
it's
some
responsible.
employee just threw it over and it cost them $500,000. Yeah. Now in these countries, either they don't have the regulation or they do have the regulation, but it's not enforced. And this is a drastic problem that we have in many of these countries. It is a human factor at the end of the day, is in the corruption in the system, the systematic corruption that exists in these places. And
Yeah, the
that's a
thing
big
is,
challenge.
if you were to get rid of all the styrofoam, for instance, you'd have to replace it with paper.
Mm.
And then what will happen to basically our paper supplies, so to speak?
Yeah.
How many more trees would we have to cut down?
Well, but paper is much more recyclable
Yeah, but I'm
than
saying
plastic,
that, but you
okay?
see, it leans on something else.
It does.
It's a pellet
Absolutely.
bond effect.
But that's because of the disposable mentality, the disposable culture that we're getting into
Yes.
it, in part because of
It's a
industry.
culture we
okay?
need to get
It
rid
is a culture. So that's why reduce, what's wrong with using the same cup instead of using a styrofoam, having a cup and reuse, all right? Clean out the cup and use the same cup time and again. Hmm?
I'm getting you one.
Yep.
I'm getting you a bottle, a reusable water bottle.
Oh, yes? Okay, there you
I'm
go.
excited. But we're selling them in my school.
Oh, really?
Biology club. Yeah.
Oh,
It
super.
says 1 less plastic bottle on it.
Okay.
We've got 3 left.
Oh,
These kids
really?
have Range Rovers and BMWs, but they can't buy reusable water.
Yeah, exactly.
So I'll get
You see? Right, there you go. That's the idea.
I can't sell 3 of them.
See? Yeah, get creative and get a bicycle, right? Get a bicycle. Yeah. But I'm going to show you some. Okay.
Take a reusable bottle in the supermarket, refill that water bottle, and avoid food with excessive packaging. Do it for those future generations. Next thing you know, it's safe spaces on YouTube.
Right. Okay. So a lot of this is just publicity. Oh, here's the last one.
Trash cleaning system to debut off Japanese island next year.
Okay, so this is high tech. This is futuristic.
The world's ocean with millions of tons of floating plastic garbage is set to make its debut next year off the coast of Japan. The Ocean Array platform is designed to collect plastic trash that currently floats on or near the water's surface. The 1 mile wide array features 2 large booms on either side.
1 mile.
Ocean currents to direct the plastic towards the
There's 2
central
booms that move slowly
trash is
in.
then filtered into a large trash receptacle on the back of the floating platform for recycling. With solar panels and water-generated turbines below the ocean surface, the platform is completely self-sustaining. The array will be installed near the Japanese island of Tsushima in 2016 as part of a 2-year-long trial.
See if stories that really should be animated. Suggest.
Okay, so that last little clip is futuristic, but that's how research and development works, right? Trying to couple research with industry so that it gets rid of a problem and at the same time it generates some revenue. Okay, let's move forward now into here, back into the US. This is the food industry. This is an interview that was done by the Wall Street Journal in 2014, all right? So it's now 4 years old, but I think it has a lot of merit. It's a video, it's an interview done with the 2 CEOs, the CEO of Tyson and the CEO, right? Chicken and livestock, and the CEO of Waste Management. So Tyson produces the Tyson wieners and the Tyson hot dogs, for example, very popular, all right, processing chicken, but also pig and cattle. And then Waste Management is a huge garbage industry in the US. These are the 2 CEOs interviewed by the Wall Street Journal. I found it very enlightening how these 2 industries are coupling to recycle, okay? And it will set us into the next one, which is called single stream recycling that we can do in our homes. A little ad.
In the chicken business, what do you do with all the chickens and what do you do with all that's left over and how is this actually being profitable for both of you?
Okay, so I don't want the storyline here to be though that Tyson has great track. Okay, we're going to do better than that. But if you look at our business, we bring in 2 types of raw materials. First, the animals, the cattle, the hogs, and the chickens, which we process, or the other non-protein items, and then we bring in the raw materials we need to process them, right? So on the animal side, we're incredibly efficient. All we lose is the cluck, the moo, and the point, right? So we.
Okay, so you notice on the 2 types of raw materials that they process. One is the, let's say, the organic raw material, which is the chicken, the pig, and the cattle, right? The other one is the inorganic raw material, in other words, the packaging that they use for all this, for selling the food. This is from the organic side, in other words, from the chicken, the pig, and the cattle, the only thing that they lose, that they don't recycle, okay, I don't know if you missed it, is the clock, the moo, and the oink. In other words, they recycle the whole animal. All right? The whole animal gets recycled one way or another, either for food or for byproducts. Like, for instance, a lot of it could be collagen fibers for glues and things like that. All right? But everything gets recycled, bone, teeth, you name it. So that gets recycled. The other part is the challenging part. The cardboard, the plastic, and all that they need for the manufacture of the product. And that's where waste management comes in. And that's the partnership. All right.
We create value streams for all of the parts of the animal. Some go in animal food.
So value stream, in other words, they have to make a profit.
Renewable fuel, those type of things. So if you look at that stream, we're incredibly efficient. If you look at the other raw material stream, then that's the stream that generally creates some waste. And that's where great partners like Waste Management come in. And what David and his group have done with us is both support and challenge us to be as efficient as we can and to try to create as many value streams as we can. For example, let's take our pork division. It's kind of the freshest on my mind. We began with one of our pork plants to work through what we were doing to create waste that could not be valued about, right? So it may be organic contaminants on corrugated material and that type of thing. So they work with us on
Can I
programs.
just interrupt? Can you explain that? You cannot recycle, apparently, corrugated cardboard if there's oil on it.
Right, because that's generally going to get sent back into the corrugated plants, which are then going to make packaging materials out of it. So we have to keep the streams separate and clean. So they work with us on a program where we could train our team members, the value of those waste streams, but then efficient processes to separate the plastics, the wood, the corrugated materials, and that type of thing. And so kind of fast forwarding to where we are today in our pork plants, about 70% of our waste stream is now recycled. So very efficient, and it's been a great success story.
And it really brings on the point, right? Which is, when Donnie said it, what he's doing is lowering that conversion cost, right? I mean, we can't do anything about what we can sell that cardboard for, let's use, or the plastic or metal on the back end. Those are markets that we don't set prices on. But what we can do is affect those conversion costs up front. So if we can lower the conversion costs now, even if the cardboard value comes down, it's still profitable to recycle. They can still save money doing it. And so that's what they've done. They've trained their folks to lower the processing costs, right? And that is what's going on. That's why I say you can't think of recycling as a homogeneous whole, because a business like Tyson has every incentive to do that because they can save money.
You are actually making a profit on recycling.
We cover the cost, not by much, but we make some profit on what we recycle.
And that's after taking into account even 30% that you can't recycle.
Right.
Okay, all right.
And so, but when you look at residential recycling, different animals, right? I mean, that's what we've done in the last 10 years.
So we got industrial, then we got residential, commercial, or residential.
Being the one bin, right? Remember, when recycling first started, it was sort of done the way Tyson did, which is we asked the consumer to separate it, and that drove down the conversion cost. We could do it profitably, but the problem was it was difficult for the consumer, and so you couldn't get as many consumers.
Right. Remember when we used to separate? I remember the time when we got 3 bins. I don't know if I'm dating myself, but there were 3 different bins. You put glass, plastic, and paper, right? Now, we were too lazy. That was not working out. It was too contaminated, or people just didn't bother, all right? So say, oh no, throw it in. So that is an attitude. That's a culture issue. And so the industry has realized that we're just too lazy to do that. And therefore, they've gone into what is known now single stream, that green bucket or brown, whatever it is on the different municipalities, is single stream. We put it all together there for recyclable. But even that cannot be contaminated with organic material, because then it actually becomes waste, trash, all right? And it's not recyclable. And that's what he's going to explain, sorry.
To do it. So we then move to single stream recycling, mix all the components together, and we'll recycle. We haven't done a very good job of educating the consumer as to what can be put into those bins. So the recycling rate goes up,
but contamination of the material, that cardboard with oil line goes up also because people put the wrong things in those containers. What does that do? Drives up the processing cost. The value on the back end goes down, and all of a sudden, that's how recycling
When you look
becomes
at this
unprofitable.
single stream recycling, how much of what's in there should not be in there?
You know, it depends on what city you're in, but we
We
have
have smarter
contamination
and less
rates.
smarter recycling cities.
Oh, absolutely, absolutely. We have contamination rates anywhere from 20% to 50%. When you have 50% contamination in recyclable material, that's garbage.
You see? And so again, it comes down to behavior, right? Okay. That leads, one video leads to another here. You can spend a whole lifetime watching these things. But, all right, now let's bring it closer to home. And this is a video. So waste management then does videos in different municipalities. And this is an area from Southeast Florida. You can tell from the tropical background. It's only a couple minutes, but this gets more into the nitty-gritty of what can actually go into those bins, what should go into the bins, and what should not go into the bins, okay? The do's and don'ts. Because this is where the tire meets the road at the individual level, at the family level, at home, in our own places where we can promote this with our family and friends.
We all have an opportunity to contribute to a growing recycling success story by recycling often and recycling right. This helps preserve valuable landfill space and saving precious natural resources like trees and energy. Forward-thinking companies like Waste Management are introducing and expanding single-stream recycling programs for both residential and commercial customers. Non-recyclable contamination slows down the recycling process, increases the cost of recycling, and decreases the value of the end product. And that's bad news for everyone. So to recycle right, whether using a cart or bin, do not place the following in your recycle container. Plastic bags of any kind, including grocery and
Plastic
non-food
bags.
And do not place your recyclables in plastic bags, polystyrene and foam containers, food or yard waste, hoses, extension cords, and hangers. Electronic waste, including cell phones, computer parts, batteries, and small appliances. Automotive parts, such as disc pads, tire rings and car batteries, motor oil, paint, hazardous chemicals, or propane tanks. Food, soil, and cardboard, hot and cold beverage cups, paper plates, towels, and tissues. Dishes, cooking utensils, pots, and pans, coffee mugs, and ceramic pots. And no liquids of any kind. And please do not use your recycle container for extra garbage space.
Remember, it's easy to recycle right, especially with single-stream recycling, where all recyclables go into one cart or bin. No separating required.
Here's what you can recycle. Paper, including newspapers, junk mail, magazines, office paper, and phone books. Paperboard, such as cereal, pasta, and tissue boxes. And cardboard that fits in your container. Plastic bottles and containers, including water and drink bottles, milk jugs, detergent, and shampoo bottles. Remember to empty your bins, please. Aluminum cans and steel and tin cans, and glass bottles and jars. Please note that recycling guidelines vary by community. Check your local recycling guidelines for specific details. Companies like Waste Management are working in partnership with counties, cities, businesses, and communities in our area to make recycling easier and more cost-effective. And each of us can step up too to make it happen. Together, let's all recycle often and recycle right.
Okay, so you get the picture of the do's and don'ts. Very important to be aware of it and to promote it with our folks at the local level. That's where the tire meets the road, okay? Industry has its own regulations to deal with, but at home, we either make it happen or not. Okay, one last one on creativity, and these now, it's gonna get more and more creative here of stuff of folks who have taken this seriously and actually made a career out of it. Starting with this, it's called the water wheel. This is Baltimore Harbor, there near Chesapeake Bay precisely. Look what these guys came up with. That's the water wheel.
I think there's a little bit of apprehension involved in trying new technologies. And a lot of people heard the idea and said, that's pretty off the wall. I don't know if that'll ever work. I used to walk across this bridge every day, and I would see the trash coming down the river, and I'd hear the tourists say, oh, this river's disgusting. So I thought about it every day on my way to work, and this is the idea I came up with. And my partner Daniel and I enlisted his help to help put it together and put it in on May 8th.
So here we are in the Jones Falls in Baltimore's Inner Harbor on a rainy day, standing on the water wheel, and which is behind me here. You can see this is the water wheel being turned by the current of Jones Falls, which is flowing very rapidly because we just had a pretty large rainstorm. And that wheel is turning this conveyor belt that is picking up all of this trash that is flowing down the Jones Falls. See, we've got a lot of people all want clean water.
Amazing.
Swim, recreate in water without coming in contact with trash, sewage, or stormwater pollution. And you can see a lot of that, especially online. There's a lot of concepts out there for cleaning up trash in the ocean. And just those concepts become very, very popular on and part of the power of the water wheel is that it's here, it exists. People can actually see it operate every day and cleaning up the trash. John is a huge inspiration to, I think, a lot of people. Here's a guy who solved this problem of just trashing waterways, something that thousands of us have been looking at for a very long time, and he actually had the ability to think about the problem and come up with this brilliant device. It moves kind of slowly, but slow and steady in this case is just fine. We've captured over 3 billion cigarettes. Second to that, I would say plastic bottles. We've probably captured about 50,000 plastic bottles since we installed it, and then styrofoam. Basically anything that floats.
Anything that floats.
It's completely sustainable in that it's powered by hydropower, and when there isn't enough current in the Jones Falls, we have solar panels, which provide solar powered pumps that actually pump water onto the water that's turning.
Okay, so 2 sources of energy for running this thing. This is totally independent on it. It's not plugged to the wall anywhere. It's mostly hydropower, right? You mentioned hydropower. So the wheel, that's why it's a water wheel. The wheel is turned because this is at a bay where there's a flow of water, but that flow will fluctuate whether there's rain or dry. Okay, if it's rainy, there's more water flowing through, so the wheel turns better, faster, etc. But when the flow dries down, then they need an extra source, and that's where the solar panels come in. So the solar panels are passively generating electricity, which is stored in some batteries inside the contraption, and then that kicks in when the water wheel is not turning fast enough. Then the stored electricity kicks in to an electric motor. The electric motor pumps water on top of the wheel to make it turn, and it's all self-sustainable. Yeah.
I'm going to go ahead and turn it on.
There.
Make her go. The water is being pumped in 2 stages from the harbor up into this reservoir, and then from the reservoir up into the wheel.
There.
And so that's what's making the wheel go around today, because the river, we've had a dry spell and there's not much flow coming out of the river. Even on these dry days, we still get a fair amount of trash. It's like, a couple trash cans full, but after a storm, we'll get as much as a couple dumpsters full. So the power from the wheel, the turning wheel, is transferred to the conveyor and into the rate system through a system of gears, chains, belts, pulleys. So it doesn't really care if there's a big 2,000-pound log on it or just a load of styrofoam. It just keeps on turning.
Yeah.
So here we are once again.
That's
back
torque.
to the water wheel. Seeing what kind of trash is
Here
coming
comes
over
the trash.
conveyor belt today.
Anything that floats very slowly.
Solar power. Hearing that excitement. Ultimately, though, our goal is actually put the water wheel out of business. We know that it's
Put it out of business, right?
Because it's immediate, innovative, but the real solution is that people need to change their.
we've heard lots and lots of people say, oh, the harbor will never be clean. You can never get all the trash out of the harbor. I think, you know, we're not taking all the trash out of the harbor, but we've made one big dent, a noticeable dent that's noticed by everybody who uses the harbor, who boats on the harbor, who lives on the harbor, who jogs the promenade. We had one article that said this is the most promising technology for keeping the plastic trash out of the oceans. You know, we're hoping to clean up this harbor right now. But I think we can take it to a bunch of different places and make it a valuable technology or a valuable asset, keeping the oceans clean, the rivers clean, the harbors clean. It's a dirty job, but it's a worthwhile project.
Okay, so creativity, huh? Creativity.
Green genius.
Yes, indeed. And it's at the source because the plastic that ends up in the oceans comes mostly from runoff, from river runoff somewhere. Okay, so we catch it before it actually hits the ocean. That's why it's a multi-pronged effect. One thing is dealing with the patch. Another one is you got to stop the source at some point. Okay, let's go forward now into actual bioremediation. Just a couple more videos here. And bioremediation is when we actually use nature to restore an area. This is going beyond the recycling issue. This is an area that has been damaged, typically a relatively large area. These two happen to be on line. Well, the coastline is one, and the other one is a deserted area, desertification. And how to bioremediate that using nature's own way and enhancing nature a little bit, okay? The first one is, anyone remember the Deep Horizon? Deep Horizon was that oil platform that caught fire about in 2010, 10 years ago in the Gulf of Mexico. And part of it spilled over into the west coast of Florida and Louisiana, Alabama, the whole coast there, all right? So these are some scientists looking at the impact of that, and one particular grass for recycling that oil. So this one has a connection with the wax worms that we saw earlier, and you tell me what that connection is. Sure. Advertisement. Okay.
The species we study is called smooth cord grass, and it's the foundation.
Okay. A little fast at the beginning. We have to get used to the tone, but it's a grass. It's a type of grass. It's called cord grass, but it's a native grass that grows along the Gulf of Mexico coast, all right? All of the coast of the Gulf of Mexico, whether it's US or Mexico itself. It's just a grass that stabilizes the coast, just like mangrove does for us on the East Coast.
Additional species along the coast of the northern Gulf of Mexico and along the Atlantic coast. This species is incredibly important for building land and keeping land from falling into the sea. We went out to several sites.
Get into the muck.
Heavy oiling after the so we found that the bacterial community inside the tissues of plants shifted to incorporate more bacteria that are important for breaking down oil.
Bacteria that break down oil.
This is also really important because our collaborators have found that there's also oil inside of the plant tissues that still needs to be broken down. So it's possible that these bacterial shifts are going to be important for continuing to clean up the oil spill inside of the plant.
This is Beijing. It was one of the worst impacted areas after the Deepwater Horizon spill, and we used the shoreline to test different strategies for remediating the oil, for removing it from the surface. And after remediation, I went in and planted kind of along the shoreline in different plots to compare what rates of erosion were like using different planted varieties versus leaving them unplanted after remediation. This stick right here is the back of a plot that we set up in 2011, where we were comparing planting versus not planting. and the plot extended 15 feet towards the water, and then in front of the plot was an additional 15 feet. And all that's gone now. So since 2011, we have 30 feet of erosion up until this stake. That keeps Spartina alterniflora
Where the grass was
a
missing.
very powerful ecosystem engineer, which means that it physically impacts this entire ecosystem. So just the presence of the marsh here is dependent on the ability of Spartina to hold the substrate in place.
Well, the elegance of focusing on Spartina is that whether we're here in the Gulf or on the Atlantic or on the Pacific, there's Spartina everywhere. Some Spartina have been artificially introduced and have proven to be problematic, but the native Spartina and other congeners and related species that serve a similar function, that effectively engineer coastlines, can serve similar purposes.
So now we're taking a closer look at these bacterial communities living symbiotically inside of root tissue to see if we can identify which bacteria are the best at biodegrading oil inside of plant tissue. And what we'd like to do is identify the best bacteria that we can use to inoculate plants in the future that are going to be used for restoration purposes. So instead of just putting a plant out there, we're going to put out a plant-bacterial combination. And that combination of organisms is going to help clean up oil faster.
Okay, so what's the relationship between Spartina, the grass, and the wax worms, the moth larva from the beeswax eating plastic? Exactly, it's the bacteria in the gut. Bacteria in the gut of the worm and bacteria in the root system of the plant. All right, so that's a symbiotic issue there. Just like earlier I was mentioning the saprophytes, the decomposers. Well, these decomposers are also being effective in breaking down some plastic. So that's bioremediation, okay? One last example from China, being that they are major pollutants right now on the earth, including CO2. I don't know if you remember the photographs of Beijing when they're having the Olympics, the yellow cloud sitting on top of the city, all right, the megalopoly. I've heard that in China it's estimated, we had a talk here 2 years ago at a conference, an international conference on climate, nature, and society. Did I tell you about that conference? Yeah, very exciting. I have it all on video for 3 days, and we had 2 days. We had some international speakers. One of them was telling us that he works with China and trying to reduce air pollution over there. An average of 10,000 people die in China every day because of smoke-related issues. Every day, 10,000. In the whole, yeah.
A friend of mine grew up in Boca Raton.
Yep.
And he would smoke cigarettes occasionally.
Yep.
He moved to Beijing, never touched another cigarette. Because he realized how much he appreciates being able to breathe.
In there, yes.
The impact over there, yeah,
yep.
it's expensive for him to have the filters in his apartment.
Uh-huh.
In Beijing,
Yes, I saw it.
Right.
Yes.
Yes. So those photos and videos that we see of the Chinese people riding their bicycles or walking around with a mask, that's real. You know, that's very real, and that's probably one of the most profitable industries in Japan. In China, is making those masks, bottled air, just to breathe clean air. Yeah, it's big. It's big. It's huge. Everybody used to ride bicycles, and then they became industrialized. They became they went into a market economy, but the regulations, either they didn't have the regulations, or the regulations were ignored to boom that economy. But it's all based on fossil fuels. So now try to get them off that dependency, you know, that addiction to fossil fuels, because it's still the cheapest. Coal, petroleum, and natural gas is still the cheapest source of energy for running industry. So this one is another example of bioremediation with desert. That this is up in the Mongolia, Inner Mongolia region, which is a vast region in the center of China, that is essentially one huge desert, all right?
Is it possible to turn this yellow sandbank into fertile soil?
Crops like corn, tomatoes, sorghum, and sunflowers, transforming more than 200 hectares of sand dunes into an oasis, all within 6 months.
Okay, so it's going to be a little, the beginning again, it's a little fast. Basically, what they did was they took, they developed what they call a plant paste, but he says it very fast only once. So the Chinese developed a plant paste, which doesn't say exactly what it is, but I'm just thinking my intuition is just ground up plants, all right? And they mix that with the sand and they turn it into soil. In other words, it becomes more fertile. And then the other component is that they start adding water. I don't know if it's a drip system or what, but those holes that the guy was making is because there's groundwater. Underneath the desert, there's groundwater. Plus, they took species that are living there in the wild, plant species that are living there in the wild, they're naturally drought resistant. And they synergize on those species, essentially enrich their sand with this plant paste, you know, and supplying the source of water, which they didn't mention much, but it has to be in the background, to undesertify, to try to recover the desert area, turn it into more vegetative area where plants do grow crops, actual crops. Okay, so here we go. I'm only going to show the video is 10 minutes, but I'm only going to show the first 3 minutes and then it goes into something else.
And scorching temperatures, not exactly ideal conditions to support vegetation. But turning that logic on its head is this desert in North China's Inner Mongolia autonomous region.
According to our calculation, there are over 70 kinds of crops growing here. Many are not planted by us, but they just grow themselves.
Crops
It's
like
natural,
corn, tomatoes,
wild.
sorghum, and sunflowers, transforming more than 200 hectares of sand dunes into an oasis, all within 6 months. It's all thanks to new technology developed by researchers at Chongqing Jiaotong University. They developed a paste made of a substance found naturally in plant cell walls. When it's added to sand, it's able to retain water, nutrients, and air.
The cost of artificial materials and machines for transforming sand into soil is lower compared with controlled environmental agriculture and reclamation.
The research team has big future plans. This fall, it hopes to transform an additional 200 hectares of desert, possibly more than 13,000 in the next few years.
So that's the water well.
It's promising for China. In 3 years, the country hopes to reforest 50% of degraded desert land that can be treated. By 2030, the United Nations is aiming to reach zero growth of desert farmland around the world. So
By the way, did you see, it's almost at the end, did you see the windmills? Okay, these are all windmills up here. So they're using every possible thing. So it's a combination.
The method could be promising for China.
Watch for the windmills in the background.
The country hopes to reforest
See them?
50% of degraded desert land that can be
Here,
treated.
here.
By 2030, the United Nations is aiming to reach zero growth of desert farmland around the world. So China's breakthrough experiment in converting sand to soil is promising for making land seemingly hostile to life fertile ground.
Are those natural deserts or is it from
Yes,
over?
those are natural deserts. This is part of a natural phenomenon that is occurring around the world. It's called desertification. And we see it, the biggest one, of course, is the Sahara. And it's along the equator, and it's moving north and south gradually, all right? The other region is called the Sahel, which is the intermediate. But in the Gobi Desert also, and the Mongolia, in the center of China, Inner Mongolia, and it's also spreading out. That's why this ambitious goal of the United Nations to stop the growth of desertification by 2030, all right, which is basically, it's analogous to restoring the coastline, but here the desert coastline, all right. So it's a combination of 4 factors, if you notice. First, that plant paste, which mixed in with the sand, turns it into soil. In other words, there's more fertility there. Secondly, these oil wells that they're punching through the sand, tapping into the groundwater, all right, because they need irrigation for these plants, at least to get them started. Third is the energy source in the background, which they don't talk much about, but those windmills are generating electricity to run some of the pipes, some of the pumps. I assume they're electrical pumps to run the irrigation system. And the fourth ingredient, which again, they have lots of, is labor. This is labor intensive, right? Generating all those plots with little sticks and bamboo and so forth, and planting all that by hand. That's definitely labor intensive, which is the fourth ingredient, let's say, that they have lots of. To do this in other developed countries, the hourly rate for these people will be astronomical, so maybe it doesn't pay off. And that's why for them, it's easier to go this route than the other routes of more developed countries. Is basically the cheap labor that they have. Okay. But you know, as far this is an artificial forest, as you can see, being claimed from the desert, and it's promising. See how it's labor intensive? But if it works for them, at least this is something that they're reclaiming the desert. And if these crops, which naturally grow there, they are drought resistant, then they produce some kind of produce, typically grains. Okay, this goes into another issue with water and so forth. You can watch the whole video if you want later. It's about 10 minutes. And overall then, this is called bioremediation, all right, which is going beyond just recycling, is trying to restore damaged areas of the world, whether it's on land or in the ocean, by trying to use nature's way, but enhancing it a little bit so that nature can begin to restore itself. And that's another beauty about nature. When we leave it alone, it tends to restore itself. So just to recap briefly here, when we go to human trash, which is the added factor in nature, we have to help nature because nature is not used to this artificial production, whether it's in the CO2 area of the gigatons there, the 9 gigatons per year, or in solid waste, these 5. The first 3 of these 5 groups are easier to recycle. Wood can be broken down into wood chip that can be used either in nature or to make fiberboard or even cardboard, etc. Metal can also be recycled sooner or later, broken down into smelt and heated up, right, and remolded. Glass also can be broken down and reheated and remolded, but plastic and electronic parts, these are the 2 big challenges, all right? We can all do our part in trying to recycle that. Again, the 3 key words: reduce, reuse, and recycle. Okay, folks, thanks a lot. So that's the end of today. I'm now going to, let me pause here so we can keep whoever is online on for a moment.